Swayam Prabha. Digital India. Educated India.
Can I write this as the value of the amplitude of the wave traveling in the negative x direction at x equal to L? Similarly, this is V plus of L, that is at x equal to L. So from this I can write gamma D is equal to V minus okay. So now this is the value of the amplitude of the wave traveling in the negative x direction at the load end. So it's here. Now this I can also write it as okay. And what is this quantity? This is nothing but the reflection coefficient at the load end. So then the value of gamma D is given like this. And if the line is lossless, then gamma D is equal to gamma L e raised to j 2 beta D. Now what does this mean graphically? Graphically what it means is, suppose this is my, now note gamma, capital gamma can be complex, right? It's a complex quantity. So if I plot gamma, so this is imaginary value of gamma, this is real value of gamma, okay. Now say initially my gamma L is here. Now when beta D changes, so, or rather I should say when D changes, so D is the distance from the load end, right? So when this is the value of gamma D when D is equal to 0. Now as my D increases, the phase becomes more negative. So negative phase means the locus that will be traced as D increases will be along a circle, okay. This is a circle and the radius of the circle is equal to modulus of gamma D. This is equal to modulus of gamma L. So the amplitude of, or the modulus of gamma D doesn't change. However, the phase changes, and that's why the locus is a circle. Okay. Further, note that when the phase or when the distance changes, so if I go from 0 to D, that is initially the distance from load end was 0, now the distance from the load end is D, whereas the phase of V minus changes by beta D, the phase of V plus changes by beta D, isn't it? That's what we saw here. Here, if the phase of let's see, our V of D is given like this. This also follows from the equations that we have just written, or what we had written while solving the transmission line equations. So the phase of V plus D will change by beta D when I go from 0 to D from the load, but the phase of gamma D changes by 2 beta D. Okay. So in other words, with the reflection coefficient, if the reflection coefficient phase changes by 2 pi, the phase of this V plus and V minus can change by a maximum of pi. So in other words, and that's how that periodicity, when the periodicity that we saw, that the input impedance of the transmission line repeats after every pi. If the input impedance repeats after every pi change in phase, then gamma D, then from intuition, simply even without going into any mathematical derivation, you can say that gamma D should also change after every change in phase by pi. So this relationship proves that because the maximum angle that can be traversed along a circle is 2 pi, right? And this is double the phase change in the transmission line. This is double the maximum, or double. So if 2 pi is my total phase change in gamma, then the maximum phase change in V plus D or V minus D will be pi. And this is one other way of proving the periodicity, that the transmission line, all the properties of the transmission line repeat after every pi phase change. So this is a very important aspect when we shall be discussing Smith chart, because it means that every change that we make in a transmission line has to be within pi phase change, and we saw that pi corresponds to lambda by 2 length change. So whatever change in the value of the impedance of a transmission line has to occur within lambda by 2 change in the length, which is equivalent to saying all change in impedance has to happen within a phase change of pi within the transmission line. So the next topic that we shall be discussing is the power dissipated. What is the total power dissipated in a transmission line? Now, before going to the power dissipated, I want to mention one other important thing that we have already discussed, is that we saw that if we go away from the load end of a transmission line towards the source end, then only the phase changes, isn't it? The magnitude of the gamma remains the same. Further, note that for increasing values of D, our phase becomes more negative. So if I go D distance away from the load, my phase of the reflection coefficient will decrease by 2 beta D. So in other words, negative, if I say once again, if I go away from the load, my phase changes by 2 beta D for D distance away from the load. So in other words, for D distance away from the load, my phase will decrease by 2 beta D. Decrease of phase means going in the clockwise direction. So in other words, when I move away from the load end, I move clockwise along a circle whose radius is equal to modulus of gamma L for a degree total phase angle of 2 beta D. Okay, so going away from the load is clockwise by 2 beta D. Going towards the load is anti-clockwise. So I can write it here. Going towards the load, this will be away from load, or towards generator, and going towards the load is like traversing anti-clockwise along this circle by a phase of 2 beta D. So I can say this is towards load. Okay. Now this is very important. So the next important, as I said, we'll discuss now about power dissipated. So the recall that the power dissipated along a transmission line so gamma L is the reflection coefficient at the load end. This is a transmission line with characteristic impedance Z0 and propagation constant beta. Power delivered to load is this is if V and I are expressed as RMS, or this is equal to okay, and then so suppose at a certain length the amplitude of the wave traveling in the positive x direction is v plus x, and the amplitude of the wave traveling in the negative x direction is v minus x. Then this is equal, so this is the I'm sorry, this is just correct this. So this is equal to gamma x magnitude square. This is the input power, okay, at this distance. So V minus X represents the reflected voltage or the reflected wave. So if I just find out the value of this quantity, then it represents the power flowing in the plus X direction, whereas this quantity represents the power flowing in the minus X direction, isn't it? So this is one important concept. Before going into the derivation, I want to reiterate this, that in microwave engineering, we consider power to have a direction of flow. Not that power is a vector quantity, but power flows in a particular direction. So here the net power that flows, say in this direction, will be the difference of the power flowing in the plus X direction, this power, and the power flowing in the negative X direction. And that is reflected here. This quantity represents the power flowing in the plus X direction had there been no reflected wave. So I can say this as the P plus at X. Okay. Okay. Now what is, so this is the power flowing at X, right? This value. So similarly, I can now write, instead of X, if I try to find out the power at a distance L from the source, which I call power flowing to the load, isn't it? So at this end, I have P plus of X of L flowing into the load, and so this is the power flowing into the load, and P minus of L, the power flowing back from the load, and the net power that is delivered to the load is the difference between these two quantities, and that is what we are getting here. So this is PL plus of X 1 minus gamma X whole square. Okay. So this is the equation for the power flowing into the load. Okay. Or I can, in fact, I can also write this as, so writing this as L, and this whole quantity I can write it as power delivered to the load. So the power delivered to the load, it is here, power delivered here is equal to this expression. This expression shows that the power delivered to the load is the difference of two terms. One, the power flowing in the positive X direction, and the other, that is this power that is flowing in the positive X direction. From this, the power flowing in the negative X direction, which is represented by this quantity, this quantity represents the power flowing in the negative X direction, because this is equal to P minus of L. Okay. This is an important relationship. You know, when we discuss microwave engineering, a term that we come across very frequently is this term, matching. You might have come across something called conjugate matching. These two terms are related but slightly different. So conjugate matching is like this. So you have, say, a generator with a internal impedance ZG, then the load that should be connected for maximum transfer should be the conjugate of ZG. Okay, but when we talk about matching as far as microwave engineering is concerned, it means a configuration where okay, so in other words, a load, say if there is no reflection, if mod gamma x is equal to 0, then such a circuit is said to be matched. In this case, I want to make one more slight correction. This should be L. Okay, so this is the reflection coefficient at the load end. In fact, I might even change this to this. Okay. Okay, so that is the condition of matching. That is when the reflection is 0, that is the entire power flowing in the plus x direction is delivered to the load. Such a circuit is said to be matching. So this is slightly different from the conjugate matching. Conjugate matching is only related to the source internal impedance, source generated internal impedance, whereas matching in microwave engineering is related to the power flow. Okay. Now coming one important relationship I want to establish for a transmission line. Say it is, again there is a load ZL connected. Okay, again this transmission line has two parameters, Z0 and theta. So Z the value of input impedance Zin at a particular distance x from the source, and suppose at this point the amplitude of the wave traveling in the positive x is v plus x, and the amplitude wave in the negative x is v minus of x, then Zin of x is equal to v of x upon I of x, and we know from transmission line theory that this is equal to v plus of x plus v minus of x upon v plus of x minus v minus of x upon z0, which in turn is equal to and this is equal to z0 okay. Now at this point, at x equal to L, z in of x is equal to zl. So then z in x equal to L is equal to zl, which is equal to z0 1 plus gamma L 1 minus gamma L. In place of gamma L, let me just call this gamma L, with L being a subscript. Okay, so from this expression I can find a value for gamma L, which is equal to ZL minus. So this is equal to, so this is an expression for the reflection coefficient at the load end. Okay, so when so the value of the reflection coefficient at the load end is simply given by this expression. Okay, so this is the first part of this lecture. In the next part, we'll cover the Smith chart. Hello, welcome back. So in this second part of this lecture, we'll be covering the topic of Smith chart. So what is this Smith chart? So Smith chart, the concept of Smith charts with what we call a bilinear transformation. So what is this bilinear transformation?